All right. Greetings, everyone. I'm Noor, organizer at the ISDAIOT 2020. I'll be moderating this session. We are in the 8th week of the ISDAIOT Symposium supported by the IEEE Victorian section. A bit of housekeeping stuff before we get started. This is going to be a 45-minute talk followed by a Q&A session in the last. Please use the Q&A window to type your questions during the talk. You may also raise your virtual hand from the bottom tab at the end of the talk so that we can unmute you if you like to ask your questions directly. For any other queries, use the chat window to write to organizers. All right, so we are privileged to have Dr. Punit Rathore to deliver some valuable insights on big data clustering with urban analytics today. Dr. Rathore is currently a postdoctoral researcher in Sensible City Lab at Massachusetts Institute of Technology, MIT, USA, where he's working on urban analytics and spatiotemporal data mining. Prior to this, Dr. Rathore was a postdoctoral researcher at GRAP NUS AI Lab at the National University of Singapore, where he worked on transportation-related problems, focusing on driver behavior analysis, driver profiling for taxi allocation, and location modeling. Dr. Rathore's research work has been internationally recognized with multiple Best Paper Awards at renowned IEEE conferences and Best Thesis Prizes at IEEE SMC Society and MSc University of Melbourne. I also take pride in stating that Dr. Rathore is the alumnus of IEEE University of Melbourne student branch. He has been a part of this community during his PhD at the university. Without any delay, let me hand over the session to our esteemed speaker. The session is all yours now, Dr. Rathore.
Thank you, Karishma, for your kind introduction. So today I'll be giving my talk on my research that I have done during my PhD and currently at the postdoc on big data clustering and the urban analytics, mainly for the smart city applications. So before we start, briefly explain what is the big data and where does it come from. So big data generally is like a pile of information, or the huge data generally in the order of terabytes or petabytes. Even sometimes it is not possible to store such amount of data on your local machine or single machine. And where does it come from? So it comes from several sources such as sensors, the crowdsourcing data. Nowadays, everyone has a smartphone, so everyone can share the data. Lab experiments, social media, of course, Facebook, Twitter, YouTube generates lots of amount of data, enterprise data, and of course, the Internet of Things, which is also known as IoT, kind of network of interconnected devices through internet. It generates lots of data, mainly for smart city applications, environmental monitoring, or several applications. How this data is useful? Many companies and governments use this data to analyze and get some useful knowledge from this and use it for the policy making, for better customer services, for decision making to implement effective policies, and of course for their business benefits. But to get the knowledge from this big data, it requires some analytical algorithms. But there are some challenges. Although there are many challenges, but the most important 5 challenges are: first is the volume. Generally, the big data is very big in the size. Of course, I discussed. Unlabeled, we generally don't have the prior information or some background information about the level of the data. So the data usually come as unlabeled. The variety, since data can be audio, video, text, speech, GPS coordinate, tweets, it can be anything. So there is lots of variety data from different sources like smartphones, Twitter, sensors. So it's a variety of the data. Since most of the data comes from the public sources, from the smartphones, of course, it will be noisy, and the data keeps coming from the several sources. So it has the velocity, means data keeps coming. So we need to process this data in the real time. So these are the main 5 challenges. So to deal with these challenges, the algorithm should be first unsupervised, means it should require no supervision or almost minimal supervision to handle the unlabeled data. It should be scalable, means we should be scale this algorithm so that it can handle the big data, means it should have ideally the linear time complexity. Of course, to make it faster, it shouldn't compromise with the accuracy. So it should be fast as well as the accurate. Efficient, we should have less resource requirement to handle the big data. And of course, we should be able to handle the streaming data. And the last one is the adaptability. The algorithm what we develop should be generalized so that it can be used for any applications with minimal tuning parameters. These are the 5 most desirable properties to handle the big data. So when we talk about the unsupervised algorithms, the most popular algorithm that strikes in our mind is the clustering or the cluster analysis. So clustering is basically to partition the data or find the groups in the data so that the points in each group are similar to each other and the points in different groups are dissimilar with each other, which is known as clustering. And it has mainly 3 problems. One is the pre-clustering. So if you see here one example in the 2-dimension, how many clusters can you see here? How many groups of the data points? Of course, you can see 3 groups of the data points or 3 clusters, but in computers, see 3 clusters? No, unless you tell computer. So there is the requirement of algorithm to find out how many clusters are there before actually clustering the data, if there is any cluster or not. Sometimes even if there is no clusters, we tend to find some clusters, which is not desirable. So to find the number of clusters before applying any algorithm is known as pre-clustering. Once you know the number of clusters or the number of groups, we can use any clustering algorithm. There are thousands of algorithms. We just supply this information and the computer algorithm will find you 3 clusters. You can see here, the algorithm, let's say k-means, can find these 3 clusters surrounded by circles, basically 3 clusters in the algorithm once you supply k. The last phase is, as I told, there are thousands of algorithms. Each algorithm can give you different results, and even with different parameters, there will be different results. So how do you know which one is the best results and which algorithm is the best? So it depends on the data. So to find out the best solution from all the available solutions is known as the post-clustering problem. So in my PhD, I developed the algorithm for each of these 3 problems separately for the big data. So before explaining my algorithm, I will briefly explain how I represent the data. So generally the data is represented in the form of feature vectors, or we can say metrics. So you see here metrics. Here the rows are basically the samples, or we can say different observations, x1 to xn. And now each observation is defined by some features. We also say dimension. So x1 is defined by like x11, x12, x1p. So we have p dimensions. A simple example is given just below this matrix. You can see it's like around, we have 5 observations from the fruits, and we have 4 features like color, size, shape, and taste. So depending on these 4 features, we want to find which fruits are similar. So we can find out, right? So in this case, we have 5 samples and 4 dimensions. So basically the data is defined by the cardinality, which is also known as the number of samples or number of observation, and P, which is basically the number of dimensions or number of features. Another form is the dissimilarity matrix. So we can also compute the difference or the dissimilarity between objects. So if we consider this matrix, the dissimilarity matrix, here 0 is basically D11, the dissimilarity of an object with itself. Since the object can be similar, it will be 0. The D12 is representing the dissimilarity between object 1 and 2, 1, 3 between 1 and 3, and so on. Since the diagonal elements represent the dissimilarity of an object with itself, of course, the diagonal elements will be 0 and the non-diagonal elements will be non-zeros. So most of the algorithms are based on the visual assessment of cluster tendency, which is also known as weight algorithm. I will briefly explain how does it work before going to my algorithm. I will explain it with the small number of data points, just 5 data points. So let's say we have this 5 by 5 distance matrix or dissimilarity matrix where the diagonal elements are 0, showing the objects are similar, and other values are less than 1. So, and let's say if you want to plot the image of this matrix in such a way so that white represents 0 and black represents 0 and white represents 1, and anything between 0 and 1 is represented by a grayscale color in that image. So if we just plot these values in a grayscale image, you can just see a checkerboard image, which doesn't give you any fruitful information. But what if we can reorder the rows and columns of this matrix such that if this reordering in such a way so that the objects which are very similar comes closer in the ordering than the objects which are dissimilar. So let's say the object 2 and 4 are very similar, so they are near, than the object 5, which is much dissimilar. So we can get this kind of ordering, which is also known as minimum spanning tree, using various shortest path algorithms. So once we know this ordering, we reorder the rows and columns of the matrix, and now we get, and again, if we plot the image, we get the new image. Now you can see these dark blocks are all aligned along the diagonals. And now we can see 2 dark blocks clearly along the diagonal. One is the bigger one on the lower side, and the one is the smaller one. So basically, we can see the 2 data points belong to the first diagonal block at the left, top left, and the 3 data points belong to the bottom right dark block. So basically, these dark blocks along the diagonal in this weight image represents the potential number of clusters. So we can visually see, okay, there are 2 clusters. So now we can supply this K in any clustering algorithm to find the 2 clusters for us. The quality of this image, what you see here, can be further improved by some distance transformation, which is also known as improved version of weight algorithm, also known as IWeight. And now you can see the weight, the quality of the image is much clearer and much sharper than the previous algorithm. But here is the problem. Here we just see for the 5 data points. What if you have millions of data points? The size of the matrix is 5 by 5. For the millions of data points, the matrix size will be million by million. Can you see this big image in your computer? Of course not. Can you store it on your device? Of course not. So it has the square complexity and you cannot store or visualize such large image. So that's why I proposed an algorithm for the big data to handle the big data and find out the number of clusters and do the clustering for the big data. So when I say big data, the big data in my case are the big in the both aspect. Number of samples means we have millions of the records, and of course they are big in the dimension, means we may have 1,000 or 100 dimensions. And to deal with this kind of challenges, I leverage two kinds of technique. One is the sampling technique, specifically smart sampling technique. I call it small because in compared to random sampling where we need more data points, in the smart sampling technique, we just require a small size sample from the original big data, which is as representative as in the original data. Means it gives a similar cluster distribution what is available in the original data. And to deal with the dimension, I use dimension reduction technique, specifically the random projection, which can reduce the dimension from higher to the lower one, or alternatively, we can say we can get the most important dimensions using any dimension reduction technique. Briefly, I will explain here the smart sampling technique that I used in my work, which is known as maximum random sampling technique. I will briefly explain it here with a small 2D example. I am intentionally choosing a two-dimensional example because you can see what is happening here, but it can be equally applicable for any high-dimensional data set. Assume here what you see here is the big data, and you can't apply weight or I weight to find the image. Basically, you cannot get the how many clusters are there. Now I apply a sampling technique. So what I will do, I will first select a random object shown in the red star from this data. And let's say this is the random object I picked from here. Now I will find an object which is furthest from this object. So this red one is the furthest from the random one. You can see this one. Then I discard the random because it was a random. Now I select the second furthest object from the first one. So now the second one is here. Now I will find the third one, which is furthest from the previous two, which is here, and so on the fourth one and the fifth one. Maybe I can do more, but I can stop here as long as the number of objects that I'm finding is greater than the some random estimate of the number of clusters. I'm fine. Here you can see I have selected at least 1 point from each clusters. Once I get these red points, I will randomly sample the points across near these local points and find these black points. So basically they are in the same proportion what in the big data. So if I take this sample out, this is what I get. And the size of this sample, small n, is much, much smaller than the capital N, which is the big data. And now I can apply weight algorithm and see, okay, there are 4 clusters. So without basically operating on the big data, I can operate on the small data and still find out that there are 4 clusters and then do the clustering. So when I say big data, it can be big in the 2 aspects. Big when the data is static, means you already have the data on your machine and you just need to operate on it. Other thing is the streaming data. Data is just coming in the streaming form and you need to process on the go, on the fly. The example is most of the time data comes from the IoT networks, sensors, smartphones. It comes on the cloud and then you need to fetch data from the cloud and process in the real time. Why in the real time? Because generally the clusters in this data appear or disappear over the time. And if you miss the information, it's not desirable. Second thing, most of the interesting events in this data appear in the form of clusters, or we can say anomalies. So the problem in this case to find the anomalies or change in the cluster structure in the high velocity streaming data. And what is the anomaly? Consider this example. You can see here data in 3 dimensions, power, temperature, and light. If you see the normal data points in the blue, it's a big cluster, and there is one small cluster on the top in the red, which shows the abnormally high power usage data points. We can say here it is abnormal or anomalous. Why? Because first, it is far away from the normal cluster, and second, the number of data points in this red cluster is very small compared to the normal data point. So how we'll find the anomaly? We will cluster the data. We will find the clusters which are far away from the normal clusters, and if the size of the cluster or the number of data points in the cluster is too small, we can say this is the anomalous cluster. So I developed an incremental part of weight algorithm for this to handle the streaming data. So in this case, I handle the data in chunks. So I just wait for the 500 data points to come, and then I operate on the 500 data points. So let's say I fix the chunk size of the 500. So first I operate on the 500 data points. I extract a smart sample using the maximum sampling algorithm that I just discussed before. And let's say the size of the sample is 200 data points. Now I will wait for different chunks, new chunks. So the chunks will be keep coming from here. Each chunk size will be 500. And now what I will do, I will update my already taken smart sample after every chunk using the incremental sampling algorithm that I developed. How does it work? Basically, delete the least important data points from the already available data, and it adds most important data points from the new chunk. So basically, it updates this chunk after every new chunk arrives. And the size of the small sample will be always 200. So even if you have millions of data points, the size of the small sample will be fixed like 200. And then we compare the sample and see whether there is any change in the cluster distribution or not. And then based on the cluster, we find the anomaly. And this is how algorithm works. So here I demonstrate through a small video on the two-dimensional. Again, I choose the two-dimension just for the demonstration. It is equally applicable for the any high-dimensional data. So you can see the data in two-dimension, but you cannot see the high-dimensional data in the two-dimension unless you compress it. But in the wet image that you see here in the top, it can give you the amount of the cluster change or the number of clusters in the form of dark blocks, even for the high-dimensional data. So I will play here, and you can see the data points will be keep coming, and the size of the dark blocks here, the new dark block will appear here, and the number of data points that keep comes, you will see it will be increasing here. How many points I'm adding? It will come here. How many points I'm deleting from the previous sample? It will appear here, and of course you can see the compression time. So let me just play this. Now see the points that keep coming. You can just see one dark block because there is only one cluster. There is no second cluster. As soon as the second cluster comes, you can see the dark blocks is increasing, and now you can see three. Now the third one arrives. You can see that there are three dark blocks. Then the fourth one will arrive. You can see now four dark blocks, and the size is also increasing based on the size of the cluster. Now this is the fifth one. Now I'm merging the two clusters on the left one, and now I will merge the two clusters on the right hand side. So you can also see the dark blocks are also merging 2 to 1. Now 5 to 4, and now 4 to 3. So you can see how the clusters are evolving or fading over the time. And you can see the very small dark block on the center basically corresponds to this second central cluster. It can be the anomaly as well. So this is how I demonstrated my algorithm for the change detection in the streaming data. Next, I demonstrated my algorithm for several smart city applications, or we also call it urban analytics. Although I worked on different domains, let's say smart transportation, smart environment, smart infrastructure, structure health monitoring, smart healthcare. But mainly I've done extensive research on the ecosystem and the transportation. So I will discuss these two domains here in this presentation. So first is the environmental monitoring. So in my lab, when I was doing my PhD, there was a deployment done for the Great Barrier Reef monitoring. So Great Barrier Reef basically is a coral reef, one of the largest coral reef in world, located in the Queensland coast in Australia, and around it hosts 3,200 coral reefs. And it is susceptible to the climate change and the other environmental stress. For example, increasing level of carbon dioxide, which can cause the ocean acidification or the increasing temperature. And because of this climate change and other parameters, there is a huge loss of coral reefs. So according to the 2008 census data, 20% of reefs were already lost, and around 15% under immediate threat, and 20% for the longer term threat. So it requires the continuous monitoring of these parameters like temperature or the carbon dioxide around this location to know the effects, how they're affecting these coral reefs. So for this purpose, there was a deployment from our lab. Basically, an IoT network was deployed on the Great Barrier Reef area for the continuous monitoring, mainly measuring the temperature, wind pressure, wind speed, and several other parameters using a IoT network. During that time, around in 2009, there was a cyclone known as Hamish cyclone. It was tracked there, and it was within the sensor network range. So you can see here, if we plot the data, you can see there was sudden drop in the pressure for 13 hours when there was a cyclone. And similarly, there was sudden increase in the wind speed during the same time. So I wanted to check my algorithm and demonstrate whether I could detect this cyclone in the hindsight if the data is coming in the streaming, if it was there. So what I did, I applied my algorithm on the actual data. Basically, the data was in the 3 dimension, the pressure, temperature, and the humidity, although it is applicable for any high dimensional data. When I applied, I found here 2 clusters. You can see one big dark block here and one very small dark block at the right bottom, which is shown in the left. And when I back projected these red points onto the data, you can see there is a green data point which I found. And when I validate with the actual data, I found this corresponds to the cyclone Hamish. So basically, if we could apply this algorithm on the streaming data on the real time, we could predict whether there is any abnormal events in the form of any interesting event. So this is one of the applications of my algorithm. The second part is the urban microclimate monitoring. So there is a phenomena called urban heat island, mainly because of the urbanization. We know many people are now moving from rural areas to the urban areas. And because of this, the temperature in the rural urban areas is increasing day by day compared to the suburb areas or the rural areas. And this effect is known as urban heat island effect because of this temperature difference. And it is not only dominant in the daytime, but also in the nighttime. So how to deal with this urban heat island effect, because it can severely affect the health of the citizens living in these areas. So one of the most common technique is by improving the urban forest strategy, like maybe improving the vegetation in the city. It can be done by increasing the canopy cover, like planting more trees in the city, improve the soil moisture or the water quality for the trees, and several other factors. One of the most common thing is by planting the trees. But how do we know which trees should be planted at what areas? Because there are different kinds of trees, they affect their microclimates differently. So we should study their microclimates, how they improve their microclimates, and of course, they have different patterns depending on the day and night and across different seasons. So to find out the microclimates, it requires continuous monitoring of different kinds of trees. So what we did, for each different kinds of species, we deployed some sensor networks measuring light, humidity, and temperature in our initial prototype. So we strategically selected 2 locations in the city of Melbourne, in the Docklands and the Fitzroy Garden. It was done in the collaboration with the City of Melbourne Council, Urban Forest Team, and the Arup. So we strategically choose the location or different kinds of trees, depending on whether the tree is near the river or near the concrete road or near the building or near the park. So we choose this location to find out the climate of the patterns. So in this purpose, we deployed 2 IoT deployment in the 2 locations, and we monitor the data for the longer period, around 6 months to 1 year. And then we use the intelligence technique to find out the patterns. This is the overall framework of the developed framework, our model. So initially, this particular layer interacts with the environment. Basically, it sends the data from the environment near the tree, and it is solar powered, means it can continuously operate 24/7 without needing any external power. Then it transmits the data to the base station, which is known as Meshlium, one of the device, through the Zigbee communication protocol. And now from here, data goes to the cloud using the 4G technology. And from the cloud, we can query the data using SQL for our analysis task. So in this particular work, I developed the 2 algorithms. One is for the spatiotemporal estimation, and the second is the anomaly detection. Once we perform this intelligence task, the results of these algorithms are presented in the visualization framework to the end user in a very simplistic format so that it can be easily understandable by the end user. And of course, the visualization is the user interactive. So what is the spatiotemporal estimation? So as I told, we deployed only just the 5 sensor nodes on the Fitzroy Garden and the 4 sensor nodes in the Docklands, which are very limited number of sensors. But we need a detailed profile of the complete area. So how can we get a detailed profile, or we can say the overall spatiotemporal map, means overall map in space, in like locations and the time. So one of the ways interpolation, but of course it does not consider many aspects like the distance of each sensor, the variability of the sensors, and whatnot. So for that purpose, I developed the Bayesian maximum entropy technique, which basically combine the data from the low precision sensors, which is usually a case nowadays for the IoT deployment. So it can consider the measurement error of the sensors, and it can combine also the high precision sensors. And what it does, it tries to maximize the information content, or the, you can say, entropy, so that we can get the optimum location as well as the overall spatiotemporal profile at the location where the sensors are not actually deployed. Using this technique, we get these two profile. The left-hand side is for the Fitzroy Garden, the right-hand side for the Dockland Library. This one is for the temperature, and this one is for the humidity. The second case was for the anomaly detection. Of course, we wanted to find out the interesting patterns from the IoT data. So for this purpose, we developed a hyperellipsoid clustering algorithm where we combined all sensor node data, and then we model this measurement in terms of the ellipsoids, where the blue ones represent the normal ellipsoids and the red ones represent the anomalous ellipsoids. And of course, they are defined by some parameters. And using some thresholding for the outlier detection, we found these two outlier, or you can say anomalous ellipsoid. And when we backtrack, we can find out what are these red points. And of course, then we can see what are the patterns. And we find out some patterns that there were some changes in the temperature. There was a little bit high temperature along the concrete roadside. And of course, there was some variation in the day and night. Once we know the result, there was a visualization framework that we developed. It was a geospatial visualization framework. Basically, a user can just select a sensor from here. A user can click here. And once user click, you can see a panoramic view. In this view, you can get an idea how many trees are there, what kind of tree is there. And then it gives us the contextual information about the tree. It will give us the canopy cover, how much canopy cover is there, like how many shades is there. And you can see the shade. And then temperature, you can see through a gradient of this color, like more blue means it is like more cooler side. If it is more red or less blue, it's like more warmer side. And the humidity is represented by the blurriness of this background. And you can see the values of these different parameters. And of course, you can compare other sensor nodes at the same time, the humidity, temperature, and the light. So this is one of the simple visualization framework that we developed for the City of Melbourne Council. The next was in the transportation side. So basically, when we say transportation in the intelligent manner, it's like intelligent transportation or the smart transportation. There are several applications. One of the application is like to find the fastest route on the network. Like in the Google, we can say what is the fastest route, to find out the parking or the taxi availability in the advance, to know the driving behavior, like what kind of driver, what is the behavior of the driver, whether he drives safe or harsh. And how can we do it? We can find the different patterns from the trajectory clustering. I will explain in the later slides what is the trajectory. Then also we can find out the anomalies. And the anomalies in the trajectories basically represent the suspicious behavior in terms of the trajectory or the vehicle movement on the road network. And if we can detect it, we can inform the authorities about this suspicious activity. And the last one is the traffic prediction. Can we predict the traffic in advance? Like how many taxis will be there in that certain road segment so that we can manage the traffic in advance. It can help the transportation agency. So how do we define the trajectory? So trajectory is basically a sequence of coordinates in the time order. Consider this example. It's a kind of trajectory from the Harvard to the MIT from the car. And this is the trajectory in the blue. And in my work, I define trajectory as an undirected graph, basically, which is defined by the V and E. V is basically intersection or nodes of the road network. In a simplistic way, I can say you these white circles on this trajectory can be considered as the node or the intersections, where the E is the edge between these nodes, or you can say this blue point between these two white circles is the edge. So a graph is the road network is defined by the V and E. So basically a trajectory is the sequence of these road networks or road segments or the road nodes. So this is how we define a trajectory in our work. So ideally, basically, we got the raw data in this format, like timestamp, taxi ID, latitude, longitude, speed, and the status. Status can be like there is a passenger on the car or the taxi, or it's free. How do we need this information? Because we want to segment the continuous trajectory into the trips. So we can find out whether there is a change between these status, like free to passenger on board or passenger on board to the free. Then we use OpenStreetMap, which is basically an open application to extract the road network for any particular city. So in our case, we use Beijing and Singapore network. So we find the road network graph for this Beijing and Singapore from the OpenStreetMap. Then this road GPS data can be very noisy. It may not be actually on the complete road. So it can be like offsite. So to match these raw noisy data points to the actual road, we develop a map matching algorithm to find out the actual sequence of the locations on the road network. And this is like one of the pre-processing algorithms. So first, I will explain trajectory clustering to find the patterns. So when we say trajectory clustering, what does it represent? So the clustering on the trajectory is basically we want to find the trajectories or the routes which are similar. So basically vehicle following similar routes. So we want to find out the more unique or interesting routes or most common routes on a particular road network. So what I did, let's consider there are different trajectories, or let's say big trajectory data. For example, we have 9 trajectories here, but you can assume it's like a big trajectory data in different directions. So the arrow you can see representing the direction, and there are different paths. What we do, I apply the maximum sampling algorithm, which is basically a smart sampling algorithm. For this big data, it will just select a small sample of size n, and you can see there are just a small number of trajectories sampled from this big data in the proportionate size. So there are more trajectories in these clusters, so it selects more trajectory from these two. Now we apply a clustering algorithm to cluster these 4 basically clusters. What we can see is the 4, and we can see there are 4 dark blocks. Basically, there are 4 clusters, and in this initial phase, we do not consider the direction. We just consider the routes. Irrespective of the direction, if there are trajectories on the vehicles trajectory on the same route, we say they are the same cluster. So you see here, even if these 2 trajectories they have in a different direction, one is here, one is here, they belong to the same cluster. Similarly for these 2 as well. So basically from here we get these 4 clusters from this until the step C. The next is we separate the trajectories in each cluster based on the direction. So now these 2 trajectories in the same cluster but in the opposite directions are separated in 2 different clusters. Similarly from here, these 2 are separated into different clusters. So now from 4 we get 6 clusters. And now we have labeled, or we clustered this small sample now, but we want to sample the whole data. So what we'll do, for each trajectory, we pick the trajectory which is not in the sample, and we find what is the nearest cluster from here and assign the same cluster here. So let's say for this one, it is nearest to the red one because of the same direction. It goes to this cluster and we get the same 2 trajectories in the red cluster. Similarly, for other trajectory also we do the same thing. At the end, finally, we get the 6 clusters for the full big data, and it can be done much faster than applying the clustering actually on the big data. So this is how we perform the clustering algorithm on the trajectory data. So these are some of the patterns that we found on the Singapore road network. So there were around 14 clusters were found. Here I show the 4 clusters from here. So this is from the Singapore road network, and you can see the red ones here basically shows a clusters, or you can say group of trajectories from city center to the airport in Singapore in this direction, and similarly the same group, same trajectories, but in the reverse direction from airport to city center. And we plot this number of trajectories in these clusters in the different time beams of 3 hours, like 12 a.m. to 3 a.m., 3 a.m. to 6 a.m., and so on. And we plot the distribution, we can find out some insights. For example, if you see the peaks of this distribution, if you see the peak of the red one, it is like around 6 a.m. to 9 a.m. It tells us that the people mostly from the city center area go to the airport to catch the early morning flights. Similarly, if you see the peak in the black one, it is around night time, or like maybe after 6 p.m. It says that most people at the airport, or you can say the visitor or the tourist, they go to the city center because there are many attractions in the city, many restaurants that they want to go to city center, so they use taxis. So this is what we get from here. Similarly, the other clusters we get from city center, which is here, to the northern suburbs, which is basically residential area in the Singapore. So when we plot this distribution, and let's say we see the peak of this black one, which is around early morning, around 9 a.m. to 12 p.m., which says that people generally leave for the work in the city center because there are many offices. They'll leave for the work from their house. And of course, there is no efficient public transport from here to here. So they rely on the taxis. So that's why we can see the peak in this time. And around there is a peak in the red one after 6 p.m. to 12 a.m. Basically, people finish their work and they head to their home using the taxis from here. So that's what we get the information. There are several other insights that we got from this work, and these insights can be really useful for the urban planners to plan the traffic, or you can say to plan the urban transportation. The next was for find the anomalous trajectory from the data. So this was we did for the Beijing data. We found around 100 anomalous trajectories, and when we see this trajectory find here, basically it represents that some vehicles are just roaming around in some small restricted area of the road network. It may be because of they are waiting for the passengers in that area. So that's why they are just hovering around or roaming around that particular segment and taking this warped, unusual paths of the trajectories. And that's why they appear as anomalous trajectories. Or it can be suspicious. It requires some domain expertise and some more knowledge to say whether it is suspicious or not. The next one is the traffic prediction, which I, of course, during I done my PhD. So what I do, the initial steps are similar until I perform clustering. So until the step this step, I know the clusters, all the unique clusters which represent the different urban mobility behavior. What I do, I train a Markov model for each cluster. So what is the Markov model? Basically, it's a first order Markov model. It represents the state transition matrix. Basically, it tells what is the probability of moving from state A to state B. Or in layman language, you can say what is the probability of moving from road segment A to road segment B. So we can train this whole first order Markov model for each unique cluster, for each unique mobility behavior. So we train this Markov model, and now let's say we want to make the prediction. So here, let's say we have this previous information, partial trajectory, we have given, and user asks what is the next location or what is the future location of this particular trajectory. So what we will do, we will consider this blue part as a partial trajectory, and then I will find the most like the best matching clusters from here. Let's say I found some cluster, and then I use the corresponding Markov model, and just I use the current locations from here, and then I see what is the next location for which I have the highest probability for moving from this state to the next state. Then I compute the next location, and then I do it like in consecutively to find until the query is performed or we've reached to the destination. And this is how we do the continuous trajectory prediction. So we computed the performance on the Singapore and the Beijing data. So for the next location prediction, I was able to find the next location with around 86% accuracy on the Singapore and around 80% on the Beijing data. For the long-term prediction, means whether we can predict the destination from the current one. So around 62% trajectory I was able to fully predict from the Singapore data, around 59% for the Beijing data. For the prediction time, it was around 6 milliseconds, which says that it can be used for the real-time prediction. And it is suitable for the dense road network like Beijing or the Singapore. In the last work on the transportation side that I'm currently doing at MIT on the driving behavior. So the driving behavior is basically how the people drive, whether they are driving safely or harshly. Of course, there can be different factors like gender, age, or several other things, but my approach is basically based on the data-driven approach, and I rely on the driving data from the naturalistic behavior. Means we don't, the data collection doesn't affect the driving, which is known as naturalistic driving data, and it is mainly based on the speed, whether there is a sudden harsh speed or not, acceleration, whether they suddenly brake or suddenly accelerate, the turning, whether there is a sharp turn, of course the location, whether they are driving harshly in the very crowded area, whether the distance from the vehicles, from like the preceding or the previous, the behind the vehicles which is behind from you. And the data can be collected from the CAN, which is controlled area network. Nowadays, it is mounted on almost all modern vehicles. And of course, the smartphones. Everybody has a smartphones. And now like Uber, Ola, they can capture the data from the smartphones. And these are now sensor equipped. We can collect sensors like speed, acceleration, and many things from the smartphones. Why do we need to measure driving behavior? Many insurance companies want to change or adjust their insurance prices and the premium prices. And let's say they want to benefit the good drivers by reducing the insurance price, or they want to punish to the bad drivers. If they are driving bad, they can increase the insurance price. Similarly, many companies like or Uber, Lyft, Ola, or Grab, they can use this to, for example, drivers training. They want to train the the bad drivers. And of course, it not only affects the driving behavior, of course, and also the maintenance. If you are driving harshly, it requires more maintenance, and of course, it can affect the fuel efficiency. So these are the many various reasons we need to monitor the driving behavior. The speed can be measured from the CAN bus or from the GPS logs from the smartphone. Of course, your time is time information, so distance by time, you can compute the speed. The speed limits vary on locations. You cannot drive on the same speed what you're driving on the highway or on the crowded area. The traffic, the weather, the same speed in the winter and the snowy area can be dangerous what you will be driving in the summer area. So these are the factors which depend the speed. So how do we know what is the speed limit should be there? So there is a software like application OpenStreetMap that I discussed, which when we can query about each location, what is the road type? It says okay, the road is primary type, secondary type, motorway, highway, street, and it can also give us the maximum speed allowable on that particular road segment. The next is the acceleration. Consider this particular case for this vehicle. The basically acceleration is measured in 3 dimensions, also known as yaw, pitch, and roll, or lateral acceleration, vertical acceleration, and the longitudinal acceleration. So when the driver suddenly accelerate or decelerate, like with the foot braking, this behavior is observed in the longitudinal acceleration because it is in the direction of the movement. So you can see the variation in the longitudinal acceleration. When the driver makes sudden left turn, right turn, on whether he shifts the lane, he or she shifts the lane, you can see the behavior in the lateral acceleration. When there is a road bumps or the potholes, you can see the variations in the vertical acceleration. So these are the different variations. If there is some harsh behavior, you can see sudden spike in one of these acceleration. And of course, the acceleration range depend on the vehicles. For the car, the safe acceleration range is lower than the truck, or even for the high inertia vehicle, it can be even higher. But for most of the vehicles like trucks and vehicles, the cars, the safe acceleration range lies between minus 0.3 G to 0.3 G, where G is the gravitational force, and anything greater than 0.5 G in both directions can be dangerous. And not only speed or acceleration alone affect can say the dangerous driving or the normal driving, but also the speed versus acceleration profile also says a lot. For example, if you're accelerating at the lower speed or if you're braking at the higher speed, it is more dangerous. Even if you are taking the left or right turn at the higher speed, it is more dangerous. So we also need to rely on the speed versus acceleration profile. So in this case, we plot this data, and you can see these red ones basically show the dangerous patterns distribution. The green is basically the safe zone, and the yellow is the neutral zone. So we can find this all behavior for the left turn, right turn, braking, and the acceleration. We can also measure the acceleration data from the smartphones, but there is some problem because the smartphone can be placed in a vehicle at different locations. It can be misplaced. So because of this, the axis of the acceleration, like XYZ, can be changed. And now we can't rely whether what is the longitudinal acceleration, what is the vertical acceleration. So that's why to deal with such kind of thing from the smartphone data, we need to virtually reorient the accelerometer data for a particular trip so that we can get the consistent acceleration in the same orientation. That's a virtual reorientation method is required. There are several methods for the virtual reorientation, and that can be used for the smartphone data. In my work, I basically find the driving behavior for the professional garbage truck drivers from the New Jersey and the Pennsylvania area. These are the professional drivers, and the company called Rover, they want to find out who are the good drivers because these trucks are very expensive, and they just want to assign good driver to these expensive trucks because maybe they can reduce the maintenance cost. And they also want to find the bad drivers so that they can train them. So we collect the data from the CAN bus, from the truck driving data, and this is the data. How does it look like? So this is like timestamp, the acceleration in XYZ, latitude, longitude, the speed, and we collect data around from 41 trucks, 54 million data points, and around 34 drivers. And we also have the ground truth information measured from a human supervisor, and the scores were given between A to F. A is basically a good driver, very good drivers. F is like very bad drivers, and B, C is anything between them. If you can say C is like average drivers. And these scores were given based on several factors. One is the violation tickets, how many traffic violations that particular driver did, number of accidents or the car crashes, and the manual observations, whether the driver is smoking while driving, whether he was talking on the phone. So there were several factors which were considered to give this score to the particular driver. We did not have much data for the E scoring, so we discard them and we have the distribution for A to F. And we convert this score A to F between 0 to 1. in our model. Then we also get this information about the maximum speed allowable for each road network. And these are the maximum speed for each kind of road network. And based on this, we compute the relative speed, basically by subtracting the actual speed with the minus relative speed. And this we got the relative speed pattern. And you can see these are like, you can say the dangerous behavior, anything greater than the maximum speed comes here. And finally, for each these features, we extract the feature using a TS library. It is a very popular library for automatic feature extraction from a time series data. And it gives us around 1892 features after the feature extraction and the important feature selection. So we get around 1892 features and this many samples. And this is our prediction framework. So we get this data, and for this collected data, basically we segment into the trips. Then we filter the noisy trips. We filter out the noisy trips. We augment the information from the OpenStreetMap. We impute the missing data. We extract the features, and then we train our deep neural network mod, which is basically a sequential deep neural network from here. And then we compute the score for each hourly session, and then we compute the oral score for each driver. And this is the score. You can see the scores in different colors, and we can find out that these histogram plots are bit distinguished from each other, and we plot it for each driver. So these are the histograms for each driver, where the blue represent the actual score and the pink histograms represent the distribution of the predicted scores. In most of the cases, you can see the mode of the histograms aligns with the actual scores, and finally, we got around 96% accuracy of this for the overall performance. Since the end user is a company which are not skilled in this deep learning techniques, they want a very simple technique. They want to see the overall performance of the drivers, who are the good ones, who are the bad ones, and they can see the bad drivers, and they can find, okay, this driver is not good in the acceleration. He is very bad in the acceleration, or he's very bad in the speed. So what they can sort by driver ID. They can go and dig into the driver, and they can see whether, okay, driver is good in the speed, he is good in the acceleration, but he's bad in this one. And it can also go how many hearts he went, and also it can explore the map, what was the area where the drivers were behaving bad. And this thing can be used to find out the coachable events, where they can coach the drivers, and of course they can assign the good drivers to the good trucks. So this is the overall end product for this for our like collaborator, the industry sponsor. And this is what currently it is undergoing. And we are also including the wearable sensor data for measuring the stress, and the optical data to see the driver's activity inside the vehicle. And it is currently ongoing process. So this is it for my work on the urban analytics. We also have positions for, if you are interested in the data analytics side or the smart city or the IoT sides, you can just go through in our website and you can apply for this position. And then if you have any questions, just feel free to ask. Thank you.
Thanks, Dr. Rathore, for throwing some light on how important clustering is for modern applications in today's world. Those were actually a diverse state of applications and data analytics applications, ranging from climate ecosystem to transportation and driving behavior. All right. So we have some questions already, and since we are running out of time, we'll get started with the Q&A session. The attendees can still ask questions using the Q&A window, or raise your hand using your virtual hand available in the bottom tab, and we will unmute you. So the first question that we have is, what is the maximum or biggest size of the data your algorithms can handle, and how fast it is compared to traditional clustering methods like k-means?
So that's a good question. So the big data, as I mentioned, it can be big, like in even size of the petabytes or terabytes, both in the number of samples and the dimensions. So in my experiments, generally we need to rely on the publicly available data. So what we found that even with the millions of data points in hundreds of dimensions, the algorithm that I developed, it was able to find out the number of clusters, or it can cluster within seconds or less than a minute time. We cannot generalize for the high dimension, like hundreds of dimension, but of course, the algorithm usually work in minutes for the millions of data points. Yep.
Okay. So thank you for that. And the next question is, this is with the champ. Thanks for the wonderful presentation. How do you manage number of IoT devices and power or battery issues in the system? May I know the brands used?
Can you just repeat the question again?
How do you manage number of IoT devices and power or battery issues?
Yeah, so that's a really good question, and for the you can say practical questions for when you deploy the IoT networks. So it depends on the several factors. One is the deployment cost. What is the budget for your deployment? So of course, in our case, it was the prototyping. So we initially deployed a very small set of the sensors. So depending on the deployment cost, you come up with the cost of the sensors, and you see, okay, this many sensors you want to deploy. Then the next task, it opens the research questions. Where need to deploy? So there's several algorithms to find the optimal locations for the sensor deployment. Okay, these are the most informative locations. If I deploy, I can get most of it. So where you deploy it. Now you want to deploy. So the deployment strategy can be on the several aspects. One, you want to maximize the coverage. Second can be you want to maximize the communication capability between each sensor node. You want to deploy so that you don't lose so many packets between each sensor node. So it depends on what is your objective for the deployment. If you want to increase your coverage, there can be a trade-off between the communication capability or the coverage. So depending on your objective, what is your objective, you need to formulate your optimization framework to find out. Generally, if you are not optimizing it, you can randomly deploy it anywhere in the locations, maybe you can say well scattered locations in your area, and then you have to rely on the communication capability of the communication protocol. Let's say for Zigbee, if the line of sight is clear, you can, let's say 500 meters or 1 kilometer, you can easily deploy. So it also depends on the specification of the communication protocol, what you're using. So you need to go to the specification. Okay, this is the range of the communication and how many packets I may lose. So you need to consider this all data sets and the specifications for each sensor and the communication protocol when you are developing this IoT network.
Thanks, Dr. Rathore. And now we have another question in the same line from Gaur. Thanks for wonderful presentation. Have you analyzed the impact of tuning the parameters in your algorithms?
Yeah, that's a really good question. So the algorithm that I discussed for the big data clustering. So let me just go through, briefly explain the part where I discussed this. So as I mentioned here in the smart sampling technique, the only parameter that was the two parameters was the K prime, which is basically nothing but the overestimate of the number of clusters. So what can you assume? Let's say data can have maximum 100 clusters. So you choose anything more than 100. So K prime can be, let's say 1000. And the sample size what you want. So let's say you want 500 sample size. So these are the only two parameters in our algorithm, and they are not very sensitive. Means even if you change by the margin of like hundreds, it won't change the performance of our algorithm. So that is the beauty of this algorithm. It is not very sensitive to the parameters, and there are only two parameters.
Thank you. And
if you want to know more about the variation of the parameters, how the performance changes, you just go through with this paper where we compared like the effect of the different parameters on the performance of the algorithm.
Yeah. And there's another question in the same line. What are the main challenges in deploying IoT networks and analyzing the collected data from IoT networks?
Yeah, so as I discussed, there are many challenges. One is the cost, deployment cost. It is the most important one. Second is the communication between the sensors. Third is the size of the data, because if you deploy more sensor nodes, you need more size, like more big size on the cloud. So you need the cloud, bigger cloud space as well. This is like on the data storage side. And then you come on the data, once your data, how to process this big data in the real time, that is another task. And the most important in the current scenario, or you can say it's trending, is the security. These IoT sensors are connected by each other. Anyone can hack this data and divert the data to different location. So the cyber security or the IoT security is the most important challenges nowadays. The people are now working how to secure your IoT deployment, because you spend a lot of money, and if someone uses this data, then it doesn't make any sense. These are the main challenges. Yeah,
I totally agree with that. So this is some light noted question. What would you use big data algorithm or conventional algorithm if you have access to a powerful computer?
Yeah. So of course, this is also a good question. So if you have powerful devices like parallel processing and your Hadoop or MapReduce kind of servers or multiple machines, you don't need to rely on the big data clustering algorithms. But let's say if you have just a small, like a conventional machine, or like one laptop or one machine, you can significantly rely on the algorithm and still get a better performance. In any way, this better testing algorithm, even on this huge parallel processing architecture, it will further boost the performance, or you can say it will further boost the runtime. So it is anyway going to benefit the computational power, even if you're machine operating on the single machine or the multiple machines in the parallel processing.
Lastly, I have one question. So how do you decide that this cluster size is anomalous? Like, do you fix the size of the cluster or smaller than
Yeah,
something, or
that's
the
again
patterns?
good question. Yeah. So when I discuss this, if you go through this paper, there are things where I discussed how do we find the anomalous cluster. So basically, it is defined. So let's say once we get the clusters, so each cluster we can compute the distance between each cluster. So maybe we can compute the centroids, and we can compute the distance, and we can also compute the number of data points in each cluster. Now there are two thresholds, alpha and beta, to find the anomalous clusters, which are user-defined threshold, and also we developed an algorithm for the adaptive selection of this threshold based on the application. So this threshold control how tight your anomalous cluster will be and how far it will be from the normal cluster. So based on this, it can find whether it will be anomalous or the normal clusters. And if to select the best parameter, you can just go through the paper, like how we select these thresholds.
Thank you, Dr. Rathore. We are almost closer to the completion time. Yeah. Thanks to the wonderful audience, and most importantly to our speaker today, Dr. Rathore. It's a great pleasure for the ISDAIOT team to organize the session. And we'll be sharing the session recording soon after the symposium. The next talk in this week is scheduled today evening at 5 p.m. on the topic Making Event-Driven Enterprise a Reality by Dr. Sam Mukhtari. We are all looking forward to seeing you again in the evening session. Until then, keep well and stay safe. Thank you.